In this video, we're going to talk about DNS, the domain name system. Now, people have many identifiers, right? A social security number, a name, a passport number. In the Jamaican context, your TRN, your tax registration number. All these things, well, with the exception of the name for people, the rest of them are numbers. Internet hosts would have an IP address that can either be 32 bits in the context of an IP version 4 address or 128 bits in the context of an IP version 6 address. These IP addresses are used for addressing datagrams. Names, like www.yahoo.com, are used by humans. So the question is, how do we map between IP addresses and names and vice versa? So going from IP address to name or from name to IP address. So the way we do that on the internet is using DNS, the domain name system. DNS is a distributed database which is implemented in a hierarchy of many name servers. DNS is an application layer protocol where hosts and name servers communicate to resolve names, that is, do the address to name translation. And this is a core internet function that is implemented as an application layer protocol. This is an example where complexity is at the network edge. Now, what kinds of services can DNS provide? Well, DNS can provide host name to IP address translation, or it can do host aliasing. So host aliasing is where you have a canonical name, an authoritative name, an alias names. So an example may be cavehill.ue.edu is really a machine at Google, for example. Or mail server aliasing. Mail server aliasing is where you have, you say cavehill.ue.edu, but cavehill.ue.edu, there's actually a mail server. If you're trying to send an email to someone at cavehill.ue.edu, there's actually a mail server responsible for that. Or if you're sending an email to uemona.edu.jm, it's a mail server that is responsible for that. DNS can also do load distribution. So whenever you do a DNS query, then you can get back multiple IP addresses that respond to one name. And then your client will randomly pick one of those addresses and open up a connection to them. Now, a question is, why don't we centralize DNS? Well, if we centralize DNS, we would have a single point of failure, that central point. We would have a high traffic volume for all the traffic that is being sent to that one point. And then the other problem is, if that centralized database is far, then you'd encounter a long round trip time trying to get to that distant database. And then there's also the problem of maintenance of that centralized database. In fact, in the early days of the internet, we just had a central file that everyone had to go to called host.txt. And that was a single point of failure. Anyway, the long answer why we don't centralize DNS is that it just doesn't scale. So the way DNS is implemented is as a hierarchical distributed database. At the top level, we have the root DNS servers, and there are 13 of these root DNS servers. And these DNS servers actually replicated across the world. So, but there are 13 of them, and they're named from A to M. Then the level below that, you have the .com DNS servers, the .org DNS servers, .edu, .jm. Okay, these are called top-level domain name servers. Okay, and then below that, you have the DNS servers for different organizations. So yahoo.com would be part of the .com tree, amazon.com, pbs.org would be part of the .org tree, poly.edu, umass.edu, ue.edu. And so if a client wants an IP address for amazon.com, the first approximation is that the client will query the root DNS name server to find the .com DNS server, and then you query the .com DNS server to get the DNS server for amazon.com. And then after that, I'll query the amazon.com DNS server to get the IP address for www.amazon.com. So I mentioned the root DNS root name servers. These are these are servers that are contacted by a local name server when it cannot resolve a name. The root name server will then contact the authoritative name server if the name mapping is not known, and gets a mapping and returns that mapping to a local name server. So I told you there are 13 root name servers. These servers are actually replicated in across the world, and they're named from A to M. Okay, so we can see A here. So that's the primary site is VeriSign in Los Angeles, but it's replicated in 4 other sites around the world. B is at the University of Southern California. It's interesting. It's also located in Los Angeles, but it's replicated 156 other sites around the world, and so on. Okay, so each server is replicated many times. Then we have the top level domain servers. These are responsible for .com, .org, .edu, .net, and so on. And all the top level country domains such as .uk, .france, .ca, .jp for Japan, .jm for Jamaica. Barbados has one as well. So Network Solutions, for example, will maintain the servers for the .com top level domain server, Educause for .edu. Uemona actually manages the top level domain name server for .jm. The authoritative DNS servers are an organization's own DNS servers, which would provide the authoritative host names IP mappings for an organization's named hosts. These authoritative DNS servers can be maintained by an organization or a service provider. Now, finally, we have the local DNS name servers, which strictly speaking will not belong to the hierarchy. However, each ISP, a residential ISP, a company, a university, will have its own local DNS server, which is also called a default name server. So when a host makes a DNS query, the query is sent to its local DNS server. And this local DNS server has a local cache of recent name to address translation pairs. But sometimes these mappings can be out of date. The local DNS server will act as a proxy and forward the query into the DNS hierarchy. So here is another second approximation, if you would, of how DNS name resolution works. Let's say the host at cis.poly.edu wants to get the IP address for gaia.cs.umass. So the contacted, in an iterated query, the contacted server will reply with the name of the server to contact. Essentially, it's saying something like, I don't know this name, but ask the server. So let's say we ask the local DNS server. Well, now the local DNS server, it's an approximation, remember? We'll ask the root DNS server, and the root DNS server say, I don't know, but ask the top level domain name server for .edu. So it does that. The top level domain name server would say, well, I don't know, but ask the DNS server at umass.edu. Here's the IP address, and so you ask the DNS name server for umass.edu, and it finally tells you, oh, that's the IP address is, Y, and now the local DNS server can tell the requesting host. Now, DNS servers can be iterative or recursive. In a recursive query, the burden of name resolution is placed on the contacted name server. Okay, so let's say here we contacted the local DNS server. If it was a recursive scenario, then the root DNS server will be asked in a recursive manner, what's the IP address for gaia.cs.umass? Now, the root DNS server will then go ahead and attempt to find, so it also ask recursively the top level domain name server for .edu, which in turn would ask the authoritative DNS server for cs.umass.edu. Now, in practice, the root DNS servers never respond to recursive DNS queries, but this is just an example. So DNS caches its records. So once any name server learns a mapping, it caches that mapping. It stores it for some time. And these cached entries will age out. They will disappear after some time. That time is called the time to live. Now, the top level domain servers typically are cached in the local name servers, which means it is very rare that the root name servers are visited. Okay, so the root DNS servers are cached here. It's very rare that we go up to the root DNS service. We might go to the root DNS service, for example, if you enter something like www.cnn.com, and instead of spelling com as C-O-M, you might spell that C-O-M-M, right? In that case, you may go to the root DNS server to find out who is responsible for .comm, for example. The cached entries can be out of date, and so when that happens, you get the best effort name to address translation. So what that means is if a host changes its IP address, then it may be a while before that change is known internet wide. Okay, it'll take a while until all the TTLs expire. There were some update and notify mechanisms specified in RFC 2136, but those are not very widely implemented. So DNS records are called resource records, and they are of this general format: a name, a value, a type, and a TTL. Okay, so if the type is A, then the name field refers to a host name, and the value is the IP address associated with that name. If the type is NS, then the name is the domain, say foo.com, and the value is the host name of the authoritative name server for that domain. If the type is CNAME, the name is the alias name for some canonical name. So for example, www.ibm.com is really server east.backup2.ibm.com, and value is the canonical name. If the type is MX, then the value is the name of the mail server associated with the name. So let's do some quick examples so we can see this. Okay, so let's fire up here. Let's say let's find the IP address for www.uemona.edu or ourvle.uemona.edu. So let's find out who that is. ourvle.uemona.edu.jm. And so we see here that ourvle.uemona.edu, okay, who is responsible, it has this IP address 196.2.1.100. Okay, let us see, for example, the name servers for ue.edu. Okay, so dig. Dig, by the way, is domain information groper. It's used to find information, basically query the DNS database. So let's see who's responsible for ue.edu. So it was dig minus t, that's ue.edu. And ue.edu, the name servers responsible for that are ns2.ue.edu, ns1, ns3, ns4, and zeus2.ue.edu. And here are their IP addresses. Okay. By the way, this is an example of load balancing where you have multiple IP addresses. So now a machine that wants to query can randomly pick one of these IP addresses for making some subsequent query, for example. Okay. Let's see, for example, who's responsible for cavehill.ue.edu. Same IP addresses, and guess what? Now the first name that was returned was zeus2.ue.edu. Okay, let's see, for example, if www.ue.edu has some canonical name. So we'll try to find a CNAME, www.ue.edu. Okay, well, we don't have some information on that. Let's see. Let's find another. I'm just making up. So, okay, here's an example. We found the CNAME for www.itc.ku.edu, and it turns out that www.itc.ku.edu, its canonical name is fiasco.itc.ku.edu, and so now you can also find the IP address for fiasco.itc.ku.edu. So we can do that by finding the A record, fiasco, and fiasco.itc.ku.edu is actually 129.237.125.27. We've also been talking a lot about gaia.cs.umass, so let's see. So let's find the canonical name for www-net.cs.umass.edu. Well, it turns out that the canonical name for www-net.cs.umass.edu is actually gaia.cs.umass.edu. And so let's see, what's the IP address for gaia.cs.umass.edu? Gaia.cs.umass.edu is actually 128.119.245.12. Okay, and the last one was the MX record. So let's see, for example, who is responsible for processing email, the mail server for uemona.edu.jm. So the mail server, mail exchanger, that's what the MX stands for, is actually xray.uemona.edu.jm. And we can find out the IP address then of xray.uemona.edu.jm. And it's 196.2.1.20. Okay, so this covers the DNS records that we're going to cover in this course. There are actually other DNS records, like there's a quad A record, that just means 4 A's. So that's for IP version 6 addresses. So like say for ue.edu. Okay. Well, in this case, UE doesn't implement any IP version 6 addresses, but let's see if there are others that might cover that. Okay, so finding it hard to find others. There. So Stanford, for example, has a bunch of IP version 6 addresses, which we can see here. Okay. Now, back to our presentation. So to insert records into DNS, let's say you have a startup, Network Utopia, and let's say what you do then to get some domain name is you're going to register your name with networkutopia.com with some DNS registrar, such as Network Solutions. What you will do, you provide your name, the IP addresses of your authoritative name server, the primary and secondary name servers, and your registrar would then insert 2 resource records into the .com top-level domain name server. And then you could also create an authoritative server type A record for www.networkutopia.com and a type MX record for networkutopia.com. Now, remember in our lecture on Chapter 1, we mentioned that there are security considerations at all levels of the protocol stack. Well, let's take a few minutes to talk about attacking DNS. So people have tried to attack DNS, and the main way they have attacked DNS is using distributed denial of service attacks. People have attempted to bombard root servers with traffic. To the best of my knowledge, none of these attacks have been successful so far, in part because many of these root name servers do a lot of traffic filtering. And the local DNS servers as well also cache the IP addresses of the top-level domain servers, so it allows one to bypass the root servers. Another way has been to bombard the top-level domain servers. This is potentially more dangerous, but most of these have largely not succeeded. And then there are redirect attacks. In this case, you might have a man in the middle, and this man in the middle, say you have Alice and Bob trying to communicate. Alice and Bob are representing, Alice would be a local DNS server, and Bob might be some DNS service trying to get some information from. Well, you could have Eve in the middle of that, and Eve will intercept the queries, and it could then give a false response. Another thing you could do is DNS poisoning, where you send bogus replies to a DNS server, which the DNS server then caches. Another thing you could do is use DNS to carry out a distributed denial of service attack. In this case, you basically send a query with a spoofed source address, and that spoofed source address is the target machine you're trying to attack. Okay. Now, for this kind of attack to succeed, you need to have amplification. In other words, you need to have many machines that are generating queries with spoofed source addresses. But people have attempted this. So this brings to an end this video on DNS. In the next video, we're going to talk about socket programming with UDP and TCP. Thank you.